All right, everybody, 10 o'clock, welcome in. Online World has now joined us. Welcome back to your favorite class. Yes, we have one costume today, Captain America. He's got his nice little shield here, pretty awesome. I realized today I have 0 orange shirts in my closet. 0. Like, I was like, come on, I at least gotta have like some Halloween spirit. I don't have any orange shirts. Dang. I was like looking through my fiance's stuff and like, I don't know if I want to wear women's clothes. I don't know, that seems a little weird. So not wearing my fiance's orange tops today. Sorry. You don't want to see that, I promise. Okay, so a couple of announcements. One, obviously we did the non-circular torsion lab today, or this week. So that's going to be due at the beginning of your lab lecture next week, and that will be the last lab that you have for this class. So that'll be your 4th lab. I think this one is probably the simplest in terms of what you actually have to put in for writing. So there you go. That's nice. Save the easiest for last. All right. That's that. Homework 7 I posted. It's on pressure vessels and thin-walled and non-circular members and torsion. So do that. That's going to be due next Friday. All right. So without any further ado, let's get into about where we left off. So last time we left off with thin-walled pressure vessels, and we had kind of finished that up with an example problem. And so today we're going to move on to thick-walled vessels. So I will share my screen. And away we go here. I noticed in the notes that there's a couple instances where I use internal radius as RI, and some instances where I use it as A. I will point those out as I move through the notes today. I'll try to be consistent with A and B for internal and outer radius as we move forward, but I'll make sure to point those out. Okay, so let's pick up where we left off, and today we're going to talk about thick-walled pressure vessels. Okay, so thick-walled vessels, kind of the picture you should have is something that looks like this. Okay, and here now we have quite a thick wall for our vessel. All right, and this is kind of like the cross-section of a cylindrical vessel. And so let's assign some variables to this particular guy. Let's say here that we have an internal radius of this guy, which we're going to call little a, and an outer radius of this guy, which we're going to call little b. All right. We'll say that the wall thickness is kind of as we have previously described. This is like little t. And so kind of for this thick-walled assumption, we're going to assume that the thickness is more than 10% of the outer radius. So for thick-walled, T is greater than 10% of the outer radius here, B. Right. Now we're going to analyze the vessel here, assuming that maybe not just we have internal pressures, but we could maybe assume that we have external pressures as well. Like let's say that we drop this into the bottom of the ocean. We got some hydrostatic pressure that's on the outside of your vessel. That could be important to analyze. So we're not going to just analyze sort of this internal pressure, which is what you might think is common. So here, this is an internal pressure, PI. But we're also going to talk about what's happening if we have external pressure as well. And so we might call this little PO. So we could have PI and PO, which is internal and external pressure. Right, respectively. Now for this particular thick-walled vessel, I'm no longer assuming that I just have a consistent state of stress through the thickness of the piece. So I understand that my derivation for like the axial stress, the hoop stress, the radial stress, etc., now is no longer going to be just some constant value in the cross section. it's going to vary as I sort of move through my cross section here from the inner to the outer radius. So maybe I can just make a note of that and say stresses will vary with R. Stresses vary along this line. Okay, so my stresses that I'm sort of interested in here, sort of my axial stress, hoop stress, longitudinal stress, etc., these are going to vary as a function of R. We'll also assume that the internal and external pressures are constant, so that again we don't develop any shear. So let's sort of make these assumptions here. So here, assume Pi and Po are constant. Okay, so we don't have like significantly higher pressure on one side than we do on the bottom side or something like that. We're going to assume that they're sort of constant in value. And so because of this, no shear stresses develop in like this R theta coordinate system. Right. Okay, so those are the assumptions that we're going to go with here. Now, we want to define, or we want some sort of equations that give us the radial stress at a point of interest, this hoop stress at a point of interest, and also the axial stress. So we'd like to derive radial stress, which we'll call sigma r, hoop stress, which we'll call sigma theta, and axial stress, sigma a, as function of r, which is the distance from center of the cylinder. And I sort of mean the central sort of axis here. All right. So let's kind of draw these things and be clear on what we're talking about. All right. So if I've got a thick-walled cylindrical vessel here, and I've got this in 3 dimensions. I'll do my best to sort of draw this in 3 dimensions. Okay, and I have some arbitrary point that's inside of my cross section. Let's say I have this point here that's point P, some point of interest, right? I could sort of draw like the 3-dimensional element at point P, like what that might look like. So let's try to draw a 3D element at P. I'll do my best here to sort of draw this, but this is going to look something like this. Okay. Where this guy is sort of like pointing back to the center of the cylinder. Okay. All right, so this is kind of like the center line of the cylinder. All right. Maybe that's a little bit more clear. And we have no shear stress, but we're going to assume that we have some of the other types of stress. So the other types of stress you might see we sort of wanted to dash this in here. Okay, it's kind of like the best I could do. So we're going to talk about, this would be your radial stress that develops, sigma r. You're going to have some hoop stress that develops on the sides here. This is sigma theta. And then along the axis of the cylinder, you're going to develop your axial stress, which is kind of like this direction and off the backside this direction, which is your axial stress. Right. So we don't have any shear stresses on this guy. That was kind of an assumption that we made because we're in this like hydrostatic kind of stress state where all of our pressures are equal. So again, I'll just emphasize no shear in this configuration. All right. So I'm just going to start with sort of a two-dimensional version of this. And I really just want to start by like looking at what is like this face here, this sort of like frontal face. Okay. So I'm going to start by drawing like a two-dimensional version of this, which you're going to see things like sigma r and sigma theta. And we'll derive some things based on that sort of like two-dimensional element. Okay, but I just wanted to show the 3D element because I think it's nice to sort of show all of kind of these stress components. Okay, so we'll start derivation with 2D element at arbitrary location from center of cylinder, which we're going to call for this derivation rho. We're going to row our boat, baby. So what's that going to look like? Okay, again, I'm just kind of like looking on the two-dimensional version of this. So here it's going to look something like this. Okay, this is pointing back to kind of like the center of the cylinder here. And I might call this like the origin or the center point O. And so this distance here is this distance that I'm referring to here as rho. For our derivation, since this is kind of like a differential element, we're going to assume that it has some like differential dimensions. And so the distance out to this location, if this is rho, I'll call this rho plus d rho. All right, so that means that this side length has a length of d rho. All right, it's kind of like the length of this portion of the element. Same on the other side. All right, I'm looking at this one particular slice, and let's say that this is just some arc length of the circle. And so we're cutting out this particular arc length here, and we're going to denote this arc length with the arc length of d theta. So with that in mind, then this length here is just going to be rho times d theta, arc length of a circle. Okay. This top length here is rho plus d rho d theta. Okay, so those are sort of my dimensions. All right. Now I'm interested in the stresses that are kind of forming in this element. When we drew them in 3D, let's now put them on here in 2D. So here we're going to have some radial stress that's developing. Here we have some radial stress that's developing. Here we have some hoop stress that's developing. Here we have some hoop stress that's developing. Okay. I'm going to write these in terms of forces. Okay. And we're going to make an assumption here that this element goes into the page at distance of dl. Some unit length into the paper, or the whiteboard as it may be here, or the writing pad, or whatever you want to call it. All right. So here, notice that we're not at like 90 degrees with what would be like the R direction. So let's talk about this by sort of like summing the forces in the R direction. And we'll say that this is just generally like the R direction. Okay. Or it's probably a little bit more clean to write it this way. So what we want to do to sort of go through this derivation is to find things like sigma R and sigma theta. We will sum the forces in the R direction equal to 0 to sort of assume equilibrium. All right. So that means that we need to sort of like talk about these blue arrows as like the forces that develop from the stresses. Right? Okay, so let's do that. All right. This guy here. This is going to be like the radial stress that's sort of like on that internal wall multiplied by the area over which it's acting. Okay. So here, the area over which this is acting is basically like this length here multiplied by that dl into the page. Right. So the force that's acting at this particular location is just that radial stress multiplied by that area. So here, the radial stress that's going to develop is sigma r. And so the force that develops is sigma r times rho d theta times the length into the page, which is dl. All right, so that's the force at that particular location. I have a similar idea for sort of the top side here. I've got this radial stress on the top, but I have an additional portion that is like d sigma r. That's kind of like the additional stress that I get from moving along the radial direction. So here the total force is the stress on this face, which is sigma r plus the differential stress that I add to it, d sigma r. It's the stress on that face, multiplied by the area over which it's acting, which here is rho plus d rho times d theta, all times dl, which is that length into the page. Trying to squeeze it in there. Sorry about that. Can I scooch this over a little? Yeah, there we go. Okay, so again, like this is the area over which it acts, and this is the stress it's developing. Okay. All right, on the sides here, we have this hoop stress, and we're going to have to resolve it since this is sort of acting not necessarily along this horizontal. There will be some component in the R direction. So if we identify that like this angle here is just theta on 2, d theta on 2, then the force that develops here, this general arrow, this is the hoop stress, sigma theta. Man, I'm going to run out of room again. Multiplied over the area which it acts, which is this d rho times dl. Okay. Same thing on the other side. Oh, sorry, d rho dl. All right, and it's the same on the other side. So that's the actual force there. We're going to have to resolve that into the r direction with the sign of theta on 2, but we'll see that in just a second. All right, so those are the forces that are sort of acting on this differential element, and now we'll sum these forces and see what happens. I'll give you a second if you're still copying this. I know that's a very involved figure, so apologies. Should have told you to make it really big. Okay, so now we'll sum the forces in the r direction. We'll take the positive values first. Here's like the positive value that we have. So kind of on the left-hand side. This will be your sigma r plus d sigma r multiplied by the area over which it acts is going to be sort of like your first force. So this will be sigma r plus d sigma r. This is sort of the stress that's acting on that top face multiplied by the area over which it's acting, which is rho plus d rho times d theta times dl. So this is like the force that's on the top of the surface of this element. This is going to be equal to all those forces that are kind of like pointing inwards in like the negative r direction. The first, obviously, that we have is this guy here, which is solely in the negative r direction. So this is going to be sigma r times rho d theta dl. And I also have components of these two forces here and here, which are acting in the negative r direction. So I can resolve those into the r direction through the sign of d theta on 2. So let's do that. So I have 2 of those, one on either side of the element. This is 2 times my hoop stress multiplied by the area over which it's acting, which is d rho times dl. And I have to resolve this into the r direction with sine d theta on 2. So there you go. That's your full force balance in the r direction. Pirate's happy in the r direction. Rawr. Okay. So we can see a couple things straight away, like the dl is going to cancel out. And goodbye. We'll assume small angle. Such that the sine of d theta on 2 is approximately equal to d theta on 2. It's a small angle assumption. And we'll assume that higher order differential terms are 0. So what I mean by that is like if I have like a d sigma r times d theta, this is approximately 0. That's what we're going to kind of go with here. That's because something very small multiplied by something very small is approximately 0. We want to only deal with the terms that are of order d theta or d sigma r. So that rears its head when you have things like d rho times d theta. It rears its head when you see things like d sigma r times d theta, etc. That's where those terms are going to pop up. Okay. So instead of sort of multiplying all these things out and actually these d thetas are also going to sort of cancel. Yes. Okay. So this d theta will cancel with this. Assuming small angle, this guy's going to cancel out as well. So that's going to be convenient. This 2 is going to cancel this 2. Also convenient. So the small angle assumption really comes in when you have these two terms multiplying each other. All right, so aside from that, if you simplified this out, you're going to end up with the following sort of equation. Here we will have rho times, let's see here. I want to make this as clear as I can. Yeah. Rho d sigma r, kind of on the left-hand side here. These two guys multiplying each other. Plus rho sigma r. And we can just do our higher order terms here. Sigma r times d rho. Is that right? Yep. This is equal to the right-hand side here. We have sigma r times rho. And we're left with this guy, sigma theta d rho. All right, that's what happens after all of our simplification. All right, we'll see that these two guys more or less canceling out with each other. And you end up with rho d sigma r plus sigma r d rho equals sigma theta d rho. Can divide by, I think this is like the first time in history I've used that actual divide by symbol. Here's your final expression. Okay. Can we identify this type of equation? This is a non-homogeneous differential equation. Okay. For sigma r as a function of rho. If you want to think of it in more clear terms, this would be like x times dy dx plus y minus c equals 0. Maybe that's a little bit clearer for everybody. No, it's probably not accurate to write this as a c. This is more like z of x equals 0. It's probably a little more clear. Complicated. Luckily, mathematicians smarter than me have solved this before. So to solve this, we need some general solution. All right. So need a general solution. That general solution is the following. Sigma r is equal to C1 plus C2 on rho squared. And that sigma theta is equal to C1 minus C2 on rho squared. All right, you put these two sort of general solutions back into what we derived up here, and your expression will be true every time regardless of the values of C1 and C2. That's what it means to be a general solution. So here's your general solution. How do we solve for the variables C1 and C2 if you have a differential equation and general solution? You guys took differential equations, right? We talked about this with buckling. Rawr. How do you solve differential equations? If you have a general solution, you need a particular solution. Youngstown. Need boundary conditions. Right. What boundary conditions can we sort of leverage in this condition? Well, we know that the radial stress at the inner wall and the outer wall of the member have to be the internal pressure and the outer pressure, respectively. And we're balancing those, so they have to be the negative of each of those. So I have two boundary conditions. Boundary condition number one would be that the radial stress at rho is equal to A, which is the internal wall, is equal to the opposite of the internal pressure. Okay, so this is radial stress balancing pressure at inner wall. My other boundary condition, you might imagine, is going to be something like the radial stress at the outer wall, rho equals B, is the opposite of whatever pressure is bearing down there. So same thing here, but outer wall. Okay, so we take this general idea, set rho is equal to A, enforce that sigma r is equal to negative pi, plug that into this equation up here, given our general solution, which is here and here. Simultaneously, plug in this particular expression into your differential equation here. And you'll have two constants that remain that you can solve for. Two equations, two unknowns, where your unknowns are C1 and C2. So we want to solve the differential equation for the particular solution. And they equate to the following. A squared pi minus b squared po all over b squared minus a squared. And C2 is negative a squared b squared pi minus po all over b squared minus a squared. All right, so that's solving your differential equation. You would get those two constants if you went through the process. So in general then, with your particular solution, remember looking of the form sigma r is C1 plus C2 on rho squared, and sigma theta is C1 minus C2 on rho squared. At any radial position, rho, the following stresses occur. If you sort of simplify this, sigma r is a squared pi minus b squared po, all divided by b squared minus a squared. minus C2 on rho squared, which is A squared B squared, PI minus PL, all over rho squared times B squared minus A squared. So that is your radial stress at any arbitrary location for a thick-walled vessel. Hoop stress. It's going to look very similar, except with the minus sign in the middle, which turns into a plus sign. There you go. So your radial and your hoop stresses, solving differential equations at that particular element. A little bit complicated, but it's not that bad. Okay. As a reminder, the domain here is for A less than or equal to rho, which is less than or equal to B. This is obviously in walls of cylinder. Doesn't really make sense if your domain is outside of the walls of the cylinder. Okay, baby. That's your radial and your hoop stress. We also have to concern ourselves with the axial stress. Which remember was like this in and out of plane dimension. All right. I wanted to get through these notes quickly today, so I'm just going to kind of present it without derivation. The derivation is fully in the notes if you'd like to take a look. Okay, it utilizes some of this like plane stress, plane strain discussion that we've talked about. Okay, so here I'll say axial stress. The biggest thing you have to really think about here is the axial stress is 0 if vessel is uncapped. Oh boy. Okay. And that's because if the vessel is uncapped, it doesn't have caps on either end. It's sort of free to expand in either direction. It's like in a case of plane stress, more or less, at either end. Okay? So in conditions of plane stress at ends. Okay? And so this axial stress equation that I'm going to write only applies if you have a capped cylinder. So if vessel is capped, you're in conditions of plane strain. Okay, at least some portion of your vessel is in plane strain. It doesn't have the ability to expand out freely to relieve that stress. So that stress is going to be maintained in that axial direction. And it will be equal to the following. There's a whole derivation for this, but pi a squared minus po b squared on b squared minus a squared. That's your axial stress. Got the sniffles. Watch out. All right. So there you go. Those are your 3 stresses. These stresses are principal. Okay. That's because there's no shear in any of these in this general configuration. So there you go straight away. Sigma R, sigma theta, and the axial stress sigma A, those are principal. All right. Last thing I want to do is just kind of show what these stresses look like in some special situations. And, the most important situation is what happens if the external pressure is 0. So that's probably the most common situation. Think of like a train car carrying pressurized gasoline or something, some pressurized air, whatever. Okay. You got internal pressure in the train cart, but outside of the train car, it's, your atmospheric pressure basically 0. Okay. So some special conditions. The most important special condition is basically with no external pressure. And things are going to simplify quite a bit. You could go through this if you want. I'll just write it here for you. The axial stress, if uncapped only, if capped, is going to be the internal pressure times A squared over B squared minus A squared. And this is still for capped only. Otherwise, if it's uncapped, the value is 0. My radial stress, if I have 0 external pressure, it's going to be pi A squared divided by B squared minus A squared multiplied by, this is 1 plus B squared on rho squared. Oh, sorry, that was the hoop stress. The radial stress just has a minus sign here. And then the hoop stress will look the same, except has a plus sign. Okay. Notice here my axial stress is not a function of rho, so it doesn't matter how far into the cylinder you go. It's going to be the same at every location. That's different than these guys, which depend on rho. So if we have only internal pressure, let me ask a sort of a theoretical question. Where will the radial and hoop stresses be the greatest? So these 2 guys here. Will it be large when the radius is small or when the radius is big? Think about this equation. Right. So this value here will be maximized when this radius is small. So where is it the greatest? What value of rho will this be maximized? At A, good. Don't say 0 because there's no material there. Remember, the domain is A to B. Right. So generally, that internal wall is where you're going to have the most stress if you only have internal pressure. Right. So that's probably the most common special condition. One other special condition you might want to talk about is not the case of external pressure only. That's kind of the same process here. But the case of no internal structure, so a solid cylinder. Okay. Well, the case for a solid cylinder, you're going to have no internal pressure. So in this case, PI is 0. I mean, it's just a solid piece. You can't have any real internal pressure there, unless you have some manufacturing issues that have caused internal pressure, like residual stresses, but we're going to neglect that situation. And in this particular case, the value of A, so here also, A is equal to 0. So you could plug these into your equations above and some stuff would happen. And you would find that the radial stress is equal to the hoop stress. And that's just going to be equal to the opposite of the outer pressure, whatever that is. They're going to be equal to each other. And you'll find that the axial stress will be 0 in this case. That makes sense. You got a solid bar of material, you have some external pressure on it. Yeah, that axial stress doesn't really have anything going on. You're just assuming that there's some free ends on it, it's uncapped. Okay, so just sort of like makes sense. And then the radial stress kind of through the center of that solid rod is just equal to whatever pressure that you have bearing down on that rod. Okay, and so it's sort of constant throughout the structure there. All right, so we're about at 10:50. I'll close it out here. I do have a nice kind of slide at the very end of the notes that sort of summarizes everything here for the general case at the inner wall and at the outer wall. So this is for internal pressure only. So maybe take a look at the notes and here you go. I also kind of highlight which principal stress this is going to be. Usually the axial stress is principal stress 2. The hoop stress will be principal stress number 1, and the radial stress will be principal stress number 3. And again, the axial stress only occurs if the cylinder is capped. There is an example problem at the very end of the notes here. I'll make a YouTube video of this example problem and I'll post it for you guys to look at. So look for that email. I'll probably do that today and I'll send an email about it. Okay, that's it for today. Hope you guys have a nice weekend. Eat a bunch of Halloween candy and etc.